Right. Okay. Seems like right now I have everything on the computer. I was just wondering how.
But yeah, so that's what it's showing.
Okay, great. Good afternoon, everyone. Welcome to class. Let's begin. I'd like to start with prayer. Is there someone who's willing to provide a prayer for us today? Get us going. Please.
Our dear Heavenly Father, we are grateful for this day. We're grateful for the opportunity that we have each week to come to campus and to study and just help us to be able to learn the things that we need to learn today, to be successful in the class and also to help us in our lives. And please bless our professor that he'll be able to be aided in his teaching by the Spirit, and that we might be aided in the Spirit in our learning as well. Please help us to be able to remember our Savior Jesus Christ and his atonement for us each and every day. And we say these things in the name of Jesus Christ. Amen.
Amen. Thank you very much. Okay, so just a comment. It is taking me some time to compile the lecture, the recording of the lecture. I still haven't been able to get the licensed version of Zoom, so at this point I'm still having to download this on a thumb drive, transport it back to my office, and then upload it. The consequence of that is that it takes at least 15 minutes for it to compile that file, and consequently my office hours I will have them today, and I will have them Wednesday, but it is going to likely be about 10 after the hour before I'm back in my office and ready to go. So just for your information. Also, I have a hard copy handout of a paper or some material on mass spectrometry. This is available online through Learning Suite, but I do have a hard copy and the TAs will distribute it. Now we will hope to talk about, or begin talking about mass spectrometry today and try to finish up most of that by Wednesday. The quiz will be available Wednesday. I will have a hard copy available in class. It will also be posted to Learning Suite, and you're able to access it. All right. I do have one individual who sent me an email indicating that he is looking for someone to work with on the quiz, to form a group with, and so I'll probably be posting that name later today on Learning Suite as well. So if you are also trying to find someone with whom to work, please consider that as a possibility. Also, if you are looking and haven't found someone and you're willing to have me post your name, I will do that as well. So I understand that it's more difficult to form these quiz groups with all the constraints that we are under currently. Okay, last time we had talked about simple separations, and by simple, I had some specific meanings for that. One was that the separations were categorical. That is, we were simply creating two groups of molecules. One group that, let's say, was positively charged, and the other group, those species that were neutral or negatively charged. So that would be cation exchange. So categorical simply means that you, at the end, you don't produce pure material, you simply produce two groups of molecules. Another aspect of simple is that it is quick and it is relatively inexpensive, not requiring sophisticated instrumentation. So when we talk about simple separations, this would not include gel electrophoresis. This would not include HPLC or FPLC. So these other methods are very sophisticated. They're much more effective in bringing about separations, but they are not simple, they're not inexpensive, and they do not produce simply two groups of molecules. Okay. Today we are going to talk about gradient elution. This is part of chromatography. Chromatography is a separation approach involving columns. Okay. At the end of last class, I talked about some cartridges that have a bed of particles in them, very small, finely divided particles that have applied to their surface certain molecules that give those particles a certain type of chemical property. So for example, we had talked, maybe the simplest of these examples would be a particle where we have modified this with some sulfonic acid groups. So these are actually covalently coupled to this silica particle, and they coat the pretty much the entire surface of this particle, and as a consequence of their presence, present negative charges outward. Okay, in a solution, an aqueous solution, is passed over these particles, this bed of resin, and those species that have positive charge will be attracted to and retained by the particles. Okay, so when we talk about cation exchange, resins, they will bind and hold cations. And so if we have a protein out here, it has some positive charge on it, it will be attracted to and retained by the this cartridge. Now, this can be expanded into columns. So these columns tend to be narrow. They tend to have a very narrow interior diameter. They are packed with this solid support with these particles. These are very, very tiny particles. Think of the most finely divided powder, flour, cooking flour that you can think of. And that would be probably as larger than the size of these particles. So they're very, very small. They're in a jacketed, a stainless steel jacketed column, because in order to get liquid to flow through this, you actually have to apply pressure. And so with something like HPLC, you can have pressures that are many times atmospheric pressure, and this is required to get the liquid to move through the column at any appreciable rate. So if we are going to carry out cation exchange chromatography, we will have a column filled with particles having sulfonic acid groups on the surface of those particles, and they will retain positive species. Now, the difference between a simple separation and what I'm going to describe here, which is gradient elution, is that instead of separating positives from negatives and neutrals, I'm now going to begin to separate positives from positives. Positively charged species from other positively charged species. Well, how is that possible? Well, it takes advantage of proteins having different amounts or different numbers of positive charges on them. We calculated the isoelectric point of an artificial hypothetical peptide. You can imagine how complicated calculation of an isoelectric point would be for a full-length protein. But it is possible to have, for some proteins, at a selected buffer pH, to have as little as, a tenth of a positive charge. Whereas something like albumin, serum albumin, may have 30 or 40 positive charges on it. And so this gradient elution is going to be able to differentiate between small differences in the net positive charge on peptides and proteins. Okay. Questions to this point? We sort of understand where this is going. We're now trying to separate similar chemical properties using small differences in the amount of that chemical property. Okay, the first question we have to answer here is how do we elute, how do we allow for positively charged proteins to be released from the solid support, from this, from the stationary phase, from these particles that are trapped in this column? Any ideas? Yes?
We could introduce like H plus to like compete, and so it'll start to release things.
Okay, so exactly. So if you didn't hear that, what he said is that we are going to add now a solution that has positively charged character. Okay, we're going to choose an acidic solution. And in fact, we can actually increase the amount of acidity as a function of time. We can start off with small amounts of acidity, so weak acid, and we can increase the amount of acidity as we pump more liquid through this column. As he mentioned, these positive charges are in competition with these positively charged, so these are hydronium ions, are in competition with this protein for these binding sites. And as we increase these, as we begin to have tens or dozens or hundreds of these for every one of these, it will only be a matter of time until our protein is eluted off of the column, comes off of that column. If you have only a small amount of positive charge, it doesn't take much acidity to outcompete it. On the other hand, if you have albumin with 30 or 40 positive charges, you're going to need a great deal of acidity to be able to release it from the binding column. Okay. Questions about that? So what this looks like is if I plot this, so if this is time, and we're talking about now solution moving through the column, and now I increase, let's say, the quantity of hydronium ion as a function of time, what will happen is that weakly positive species will come off early, and so these are peaks of material coming off. And then maybe I'll encounter proteins that have a couple positive charges, so they will come off. And then maybe those that have 5 or 6 will come off after that. And then, as mentioned, there may be some that have many positive charges. The peak height is only an indication of how much protein is present in that particular solution. So as a function of time now, I begin to separate species that are positively charged based on whether they're weakly or profoundly positively charged. This is called gradient elution. Okay. Yes?
Would the change in pH be something you want to watch out for on those proteins? Because can't some of them like change conformations at certain pH levels that would potentially denature them?
Yes, you would have to be careful. So in general, most proteins are stable to a pH of about 2.5 to 3. But below that, then you could, in fact, lose your proteins. They would simply aggregate, precipitate, they would plug up your column, you would lose the material you're trying to purify. So it would be a bit of a lab disaster. So yes, you have to be careful. Other questions?
Last time we talked about separating off the ion from the bead using like an organic solvent.
We're going to talk about that next. So that's when we use reverse phase hydrophobic columns binding to hydrophobic materials. You're great. This is a great segue. But are there any other questions before we leave this? So this is cation exchange chromatography. So yes.
There's one other question on there that said chemical process can be done with base to eliminate the product.
Yes, so if you're doing anion exchange, so instead of sulfonic acids, if I have quaternary amines that have a positive charge on them, then anionic species will be, or anionic proteins, will be retained by the column, and the same process can be done, the elution process can be done by increasing amounts of typically a volatile base. Why? Because you don't want lots of salts around if you only have small amounts of protein. So you do something like ammonium hydroxide. Here you would usually use something like trifluoroacetic acid or formic acid because they are volatile and you can get rid of them simply by drying them. You could use salts, but if you have nanograms of protein and you have milligrams of sodium chloride, you have lost your protein. There's no way on earth you're going to be able to fish it out of a block of salt. Okay, so typically then volatile acids or volatile bases, and for eluting cation and anion exchange. Okay, let's consider what was mentioned, and that is reverse phase hydrophobic interaction. So let me go here. So as talked about, we can modify these silanol groups. So these silanol groups can be esterified with fatty acids, and these we then populate the surface of this particle with C18 is the most commonly used because it's cheap and in terms of getting the fatty acids. And it gives you a very hydrophobic character to the particle. Now, any protein that comes along that has hydrophobic character will be retained by the column. So if you have something with just a small patch of hydrophobic character, then here's our fatty acid interacting with it. Whereas if we have something with lots of hydrophobic character, we may have then these much more substantial interfaces. It turns out that the size of the interface determines how tightly these proteins or other species are bound to the column. Put another way, if we have a very hydrophobic molecule and it's interacting with this very hydrophobically coated particle, it will be bound very tightly. whereas something with just a small amount of, it has a very polar surface for the most part, but a small patch of hydrophobic amino acids on the surface, then it will be bound less well. Now, the thing, remember now, and this is where we go back to your question, the thing that's holding these two together is a hydration cage. Okay, so we have here then a hydration cage surrounding here, and here we have this hydration cage here that are holding these proteins, peptides, whatever, together with the particle. So now we come to the question of, well, how do we get things off? It's fairly understandable that hydrophobic species will clump together, displacing ordered water molecules, increasing entropy, and the entropy is what holds this together. But how do we now get them off? And this is where we come to the organic solvents. Now remember, the organic solvents, in order to disrupt the hydration cage, there's only the hydration cage holding these together. If we interfere with the hydration cage, these will come off. So to be able to do that, we have to have something that is water soluble, that can actually insert itself into the hydration cage, and it has to be able to hydrogen bond. So something like methanol is able to hydrogen bond. Ethanol, isopropanol, acetonitrile is another one that is commonly used. And again, what we do is we begin to increase the amount of our organic solvent as a function of time. And what happens then is those proteins that have only a small amount of hydrophobic character, they have a very small hydration cage. It doesn't take much methanol to interfere with the hydration cage and allow the release of that particular molecule. Those that are more hydrophobic, slightly more hydrophobic, will come off later. They will require more of our organic solvent to disrupt the hydration cage. And then, of course, there are those that are very hydrophobic, and it will require much more substantial amounts of the organic solvent to release or bring about the release of those hydrophobic proteins. This method, this is called reverse phase or C18 reverse phase HPLC, is the most common purification method for proteins, bar none. You can take a mixture, if you have a really good instrument, you have a really good gradient, this is called the gradient, we're getting increasing amounts of organic solvent. You can separate a mixture of as many as 200 or 300 different compounds into individual separated species, purified species. Now, of course, when we're working with something as complicated as the cytosol of a cell or serum, you'll have tens of thousands of proteins. And so this is going to be just one step among many. Then you might go back and do cation exchange. You might go back and do anion exchange and several other ways of separating things to be able to finally isolate, purify your material, okay? So we talked about this factor that was in the roots of this plant from the Amazon that seemed to have antibacterial properties. Well, we carry out this gradient elution, and then what you have to do is you have to analyze each and every one of these peaks to see where the principle, the factor is that has antimicrobial activity. So as I mentioned, nucleic acid techniques, PCR and things like that, you can crank these out in an afternoon. But when you're actually trying to discover something that involves purification of proteins, you're talking about an investment of substantial time. Weeks, months, sometimes, sadly, even years before you can get enough of the material to be able to study it beyond that. Okay, let's take questions now. We spent quite a bit of time on this. Yes?
One of the questions on the chat was, when the size of the molecule also come into play when you try to release it, because a bigger molecule would have a larger hydration pH.
So informally, only those portions of the molecule that are hydrophobic will have this structured water hydration cage. Now, there are interactions with polar groups and water, but they don't form a hydration cage. What does that mean? Well, let's take something like a carboxylate. So we have this negatively charged species here. What we're going to have is not water molecules sort of hydrogen bonding to each other, but they will be oriented such that the positive dipole of the water is going to be oriented towards this negatively charged group here. So it's a different, it does create a hydration, let me avoid that. It creates then some water molecules surrounding these negatively charged species or polar side groups, but it doesn't form this tight hydration cage, this lattice. So back to the issue of size, with larger proteins, the likelihood of having hydrophobic character goes up. And so there is a reasonable likelihood that bigger proteins would require more organic solvent to get them off. But the basic principle is that it is the size of the interface between the column and whatever the protein is presenting to the solution that matters. Okay? Yes?
Can you just describe one more time how we can interpret the lines on the graph in the map?
Oh, these just represent different proteins.
And it's the percent of the concentration of the CH308.
This line represents the concentration or the percentage of organic solvent present that's flowing through the column at that time. Okay. Okay. I'm going to, there is actually quite a bit of material about this on the slides. So, let me direct you to that to get more information. Let me make a comment or statement about okay, the title of this is ultracentrifugation. We've got this. Let's see. All right. You will hear of people separating things using ultracentrifugation. This is where we're imposing G forces of 100,000 G on a solution. And the solution is on top of a gradient, a density gradient formed by salts or by sugars. So cesium chloride or sucrose gradients. But I just make a blanket statement that this has no value in trying to separate peptides and proteins. They're simply too light. They have too little density to actually move through the gradient. They will just stay on top of this. This is useful for separating organelles, so nuclei from endosomes, from whatever else, but it is not useful for purifying proteins. Okay, here we have lots of information about chromatography. And we've discussed it, so I'll move along now to electrophoresis. So when we talk about separations, electrophoretic separations can be an important tool in purifying proteins. This is a complicated looking formula. You won't have to remember this, but let me point out what this represents quickly. So let me go here. So if we look at this first term here, this is the mobility. So what this represents is if you have a solution and you place a voltage across the solution, a voltage drop, you will cause charged ions, charged species, to move towards the oppositely charged electrode. So if we have a protein with 2 positive charges on it, it will move towards the negatively charged electrode. The solutions that we're talking about that fill a tube or a gel have to have electrolyte in them. They have to have some salt to be able to conduct electricity through them. But the mobility of a protein is a constant. At least under defined conditions, it will be a constant. And we see here that this is due to a ratio of the velocity and the electric potential across whatever medium you are using to separate the proteins. Put another way, if I increase, since this mobility is a constant, if I increase the voltage, the velocity will increase as well. Okay? So if I increase E, V will also be increased proportionately so that the mobility stays constant. Over here, we see that we have Z. This term represents the charge on a molecule, whereas F is called a frictional component, and for our purposes, you can think of it as size. So if you have a larger molecule, it will, if the frictional component, the F, the small f, is increased, Z will have to be increased if you're going to maintain the same mobility through the solution, okay? Okay, this is very introductory. I don't expect you to be experts on this, but I'm just trying to help you understand that the size of something matters. The bigger it is, in general, if you have a constant voltage across this, the mobility will be slower. If it's smaller, it goes faster. This is fairly intuitive. And likewise, if I increase the voltage across this, this tube or gel, that will also increase the mobility of the protein. Now here's, we're going to talk about, in particular, there are different kinds of gel electrophoresis. Some of this is done in tubes. You fill it with liquid, there's no gel present, and you simply apply a voltage and things will move towards the oppositely charged electrode, and you simply can separate things. The problem with electrophoresis is that, at least in tube electrophoresis, it's hard to recover your proteins. You can see them go by, but it's hard to recover them. And the reason is that usually you have a very large volume at each end of the tube, and so it gets problematic. What we do see a lot in labs are gel electrophoresis. We have SDS Page, So we'll talk about that. And we have other kinds of gel electrophoresis where we do not denature the compounds. Okay, let's talk about SDS page. SDS stands for sodium dodecyl sulfate. So you can see that this molecule is negatively charged on one end. It has this sulfate group, and it has this long hydrophobic aliphatic side chain as well. And so these types of molecules act as detergents. They're able to interact favorably with dirt or oils here on this end, oops, and they can take these oils into solution because they have these charged head groups. And so you will surround an oil droplet with many, many copies of SDS, and you can then rinse the oil out of your clothing or whatever and use it as a detergent. But in this context, what we're going to do is we're going to interact SDS with proteins. And it's going to have a sort of a interesting effect. Now, to allow this to be fully effective, what they'll do is they will add SDS to a solution, usually an aqueous solution, of the protein, and then they'll boil it. Why will they boil it? Well, they're going to unfold the protein, allowing the SDS to interact with all the internal hydrophobic side groups. And so in the end, we have this sort of extended protein. It's no longer compact, it's opened up, it's unfolded, and we're going to get these SDS molecules populating the entire surface of or most of the surface of these denatured proteins. So because about half of the amino acids on average in any protein are hydrophobic, in general we'll get about one SDS molecule for every 2 amino acids. Does that make sense? So you have half hydrophobic and half other types of amino acids. So each hydrophobic amino acid will form and have an interaction with the aliphatic tail of the SDS molecule. So we end up coating our protein with SDS to the tune of about 1 SDS for every 2 amino acids. Now, the consequence of that is that we go back to this equation, we will have, if you notice that we will, if we increase the charge, we will increase the mobility, but we're increasing the charge proportional to the size of the protein. So the bigger the protein, the more copies of SDS will be bound to it. And as a consequence, by doing this, you convert all of or largely all of the proteins to have the same mobility. Okay? If they're bigger, they have more negative charge on them. So this ratio of Z, negative charge, to size is going to be proportional, and consequently, all of the proteins in your solution that are treated with the SDS will have approximately the same mobility. Then what you do is you take your solution of your denatured SDS-treated protein, and you will load it onto a gel. So there's a little well here that is present in the gel as you've created this using a comb. As you cast the gel, as you form the gel, as you bring about polymerization of the acrylamide. So we're forming polyacrylamide, and we have a very narrow gel. It's not very millimeter or two, well, it's a couple millimeters thick. These represent 2 glass plates here, you can see. And these 2 glass plates contain the gel. And then we load these wells and we overflow this reservoir behind. So let me change color here. So the reservoir behind is going to be filled with a solution that will conduct electricity. And I add just enough that it overflows and makes contact with the solution in the wells. Then I also have another solution that fills this reservoir down at the bottom. So the solution at the bottom is going to be positively charged. I'm going to place my negative electrode in the green solution here. And when I apply the voltage, then all of these proteins will tend to move toward the positive electrode with the same mobility. The problem is, or the feature of this that separates them, is that I have all these crosslinks. As I polymerize the acrylamide, I form all of these crosslinks. The crosslinks in turn form kind of a series of channels. And by using the right amount of acrylamide, forming the right number of crosslinks, I can create channels that are small enough that they restrict the flow of larger proteins. So in the end, what ends up happening is I apply the voltage, I wait a period of time, and I will separate my proteins based on size. Their mobilities have been made the same by coating them with SDS. Approximately 1 SDS per hydrophobic side group, but about 1 out of 2 amino acids are hydrophobic. So in the end, these become sizing gels. The smaller proteins, notice down here, we have one that has a molecular weight of about 14,000. It will travel the farthest. It's able to move through these channels with less problem than a larger protein, which has to try to find a channel that will accommodate its size. If you have proteins that are above this molecular weight, they won't move onto the column at all. They're simply too big to fit in any of the channels. If I have things that are smaller than about 14,000, they'll simply run off the end of the gel. So this is useful for proteins, but not very useful for peptides or for protein complexes that are very large in nature. You can adjust the amount of acrylamide in the gel to create more crosslinks, smaller openings, and in doing so be able to separate peptides. Or you can, to some degree, reduce the amount of acrylamide and allow for larger species to be separated. You can't reduce it too much or the gel becomes too fragile, too flimsy, and will break apart. Okay, so we've gone through this pretty quickly. Let's have your questions, okay? Yes?
Once that protein is denatured, can you ever use it again? Like, is it?
No. So, well, yes and no. So you won't be able to measure its activity. But what you can do is you can submit it to mass spectrometry and determine what its amino acid sequence is. So it's not an entire loss, but you do lose the activity, and consequently, you won't be able to carry out a bioassay to see where the compound is. So if you couple this to, let's say, our reverse phase HPLC step, we'll get all of those fractions. If I find one that has activity, this would be a good way of this would be another good step in the process of trying to purify it, is to try and move it through a gel. So, other questions? Now there are, yes, go ahead.
Just to make sure I understand this right, in this method, the proteins are already denatured then?
Yes, before you even load them onto the gel, you know, even before you start to pipette them into the wells, you have boiled them with SDS, which is a detergent and will also facilitate denaturation of proteins. And you also add a reducing agent, usually a reducing agent that disrupts disulfide bridges so that the protein really fully unfolds and you're able to coat it completely with SDS. Someone else had a hand up. Yes?
So initially you were saying that after adding the SDS, all of the proteins have the same frictional coefficient because they're all stretched out.
They have the same mobility because if they are bigger, they'll have more copies of SDS on them. So if there's one SDS for every 2 amino acids, if I have 100 amino acids in one protein, that will mean 50 copies of SDS or 50 negative charges. If I have a protein with 1,000 amino acids, then 500 of those will have SDS attached. And if I go back to this equation, I'll see that Z, that 500 over something with 1,000 amino acids is going to produce the same mobility as 50Z over something with 100 amino acids. That ratio then remains the same for the two. So if in an unobstructed tube, if I put the two together with having the SDS coating, they would move at the same rate. What happens with the gel is that the gel imposes restrictions on how fast things can move. So, if you have a big bulky thing, it's harder to move it through this maze than if you have a very small compound. Okay.
So then they're separated by size and not by charge.
That is right. The charge to size is going to be constant relatively constant for all of the proteins. What's going to differentiate how fast they move or how far they move through the gel is their size. Small things go through faster, more easily. Large things have more difficulty getting through the gel. Yes?
One of the students asked if there's any technique to separate peptides, because I know that the gel would be too.
Yeah, so, I mean, you can use the reverse phase HPLC, but you can use gel electrophoresis. You just increase the amount of acrylamide. So protein gel electrophoresis uses about 7% acrylamide. That's what's shown here in this slide. This is a 7% polyacrylamide gel. If you increase it to, let's say, twice that, 14, then you have many more crosslinks and smaller channels, and that would be suitable for separating peptides. It wouldn't work for proteins. Okay, so now you have to make rational choices about what you're trying to do. Okay, any other questions? We need to call it quits. Okay, let me begin the story. For many years, I lived in Massachusetts, and one of the sort of traditions in the ward in which we lived was that over the Thanksgiving holiday, specifically on the Friday and Saturday of Thanksgiving weekend, we would go to a place called Mount Monadnock, which is in outside of Peterborough, New Hampshire. It's a very popular hiking spot. And one of the primary reasons is that it has a granite dome, which means that you actually come out of the trees and are able to see something. Other mountains in the area, you often have a forest on top of them, and you get to the top and you can't see anything except the trees that surround you. So what would happen is that on the Friday after Thanksgiving, men and boys in the ward would typically scout age young men would go up with their fathers or scout leaders to and camp out at the base of Mount Monadnock, and then the next morning they would start up the mountain and make this climb and come back down. So on Saturday afternoon, you'd be back home, probably late Saturday afternoon. Okay, we'll have to leave it here. All right. I will be doing my office hours today, but it'll probably be in about 20 minutes. So.